We'll continue with the gas turbine cycle. And if you remember from our previous lecture, we have said that the simplest gas turbine cycle components are the compressor, then you have the heat exchanger, and then you have the turbine, and then the condenser part or the heat exchanger part removes heat, and you back to compressor again. And this was the TS diagram for the gas turbine cycle. Now I will draw TS diagram for the gas turbine with regenerator, and then TS diagram for gas turbine, intercooling, and the reheater. Firstly, the gas turbine with the regenerator. Now let's start with it. And if you remember, we have said that you have compressor here. That compressor outlet is sent to regenerator here. This one is this regenerator is a heat exchanger. Okay, this one is heat exchanger. And then from that exchanger, you have that flow that comes into the combustion chamber. This one is the combustion chamber. And then from that combustion chamber, you have the turbine. And here you have got the work, and from the turbine, the outlet is diverted into a regenerator, and where you have the heat transfer from the outlet of turbine into the fluid that leaves the compressor. And I will put some numbers here, so it will have, you will have that 1 here, and 2 is the outlet of compressor, and the 3 is the outlet of regenerator, 4 is the combustion chamber outlet, 5 is the turbine outlet, and the 6 is the regenerator outlet from the turbine. And this one, if you remember regenerator, it gives off energy of the turbine outlet fluid to the compressor. So that, but you should remember that to use regenerator, okay, T5 should be greater than T2. You should have, you should have higher temperature at the turbine outlet so that its energy can be given off to the energy of the compressor outlet. Okay. This is the main principle that we are using regenerator. Now let's draw the TS diagram for this process. One side you will have the temperature, and the other axis you will have that entropy. Okay, now let's start with the compressor one. And the compressor is isotropic device. And this one, these are the approximations for the Brayton cycle with regenerator. These are ideal. I don't have time for the real analysis, but the ideal analysis will be okay for us for the semester. So you have this reversible adiabatic compressor, and therefore it is isentropic. So you will go from 1 to 2 in an isentropic manner. And then comes the regenerator, and this one is the heat exchanger, and this heat exchanger for ideal analysis, it is taken as to be isobaric. And the pressure remains constant, but entropy and the temperature increases. T and the S increases. And therefore you will have something like this one. Okay. And this will go to state 3. Okay. And then you will have that from 3 to 4 combustion chamber, and here again you have that increase of this one is also heat exchanger and isobaric, and the T and the S increases. Okay. Then 3 to 4 you will have this chart here. Okay. And then now comes back to turbine state, which is 4 to 5. Okay. And when you drop from 4 to 5, but you should remember that this 5, that is that outlet of the turbine, should be greater than 3. If it is ideal, they can be equal. Okay, but for real analysis, the 5 should be the same, should be more than 3. So let me say that T5 greater than T3. It is real. Okay, but for the ideal analysis, T5 is equal to T3 ideal analysis. Okay, so yes, so ideal analysis means that fluid has given all its energy. Okay. So then I will drop from 4 to 5, but this one is also reversible and adiabatic, and therefore you will have this isentropic drop. Okay. But I am not increasing this 3 value here, so let me put it as 3 here, and the 5 should be less than that one. Okay, here you will have that 5. And then from 5 to 6, the value drops by the regenerator. And here you should also remember that the T6 should be greater than T2. Okay, this one is the real. Okay. But for ideal analysis, T6 is equal to T2 for ideal analysis. Okay. So this one means that fluid again has given all its energy. Okay. So for real analysis, the fluid has not given all its energy to temperature at state 2. Okay. There is some temperature. Okay. There is some energy with the living fluid, the fluid that leaves the system. There is some energy with it. But for ideal analysis, they have the same energy. Okay. This one has the same energy. Okay. And for this one also, it means that they have the same energy. But for real analysis, it is not true. So therefore, when I drop from 5 to 6, so I should have that pressure constant process, and then that 5 to 6, and 6 is more than 2. Let me draw that one here. So you will have that 5 to 6. Okay. And 6 is again more than 2. And then you will have this, and from 1 to 2, so just 1 minute, that this line should converge to a point here. Therefore, 1 should be a bit lower. It should be something like this one. Because you should at the end meet these lines. These lines should meet. Okay, so this one is 1. So 1 to 2 isentropic, and then 2, 3 isobaric, and the 3 to 4 isobaric, and the 4 to 5 isentropic, 5 to 6. And you can see that 6 has that more energy when it leaves. Okay, but for the thermodynamic analysis, it should be closed. So the ideal Brayton cycle means that it should be closed. Okay? And to make it closed, okay, so we will need heat exchanger to drop T6 to T1. Okay, you should need heat exchanger to drop T6 to T1, and that exchanger, so I will add it with a different color here, so you can see I will add a heat exchanger here. This outlet is diverted as the inlet as 1. Erase this part. Okay. And this outlet, which is at 6, and it is diverted at the inlet. And this is additional heat exchanger. Okay, so this one is that for thermodynamic analysis. Okay. Analysis. Therefore, here you will have that from 6 to 1. I'm drawing it with a different color here. Okay. Again, these lines do not meet, so it means that I should make this one as a bit longer. Okay. And this is the Brayton cycle with the regenerator. Okay, but we have said it. If it is ideal, then the 6 and the 2 should be the same. If it is ideal and the 6, therefore for ideal analysis, I can say that. Okay, so 6 prime. Okay, this one is if ideal regenerator. Similarly, and if it is ideal, 5 and the 3 should be the same. Okay, so if I do that one here, okay, this one should be that 5 prime. If ideal regenerator. Okay, now you can notice that from 2 to 3, I'm adding heat from the regenerator, and from 3 to 4, I'm adding the heat by the combustion chamber. Okay. You have 2 heat exchange, heat addition here. So this one, 2 and 3, it comes from this regenerator, and from 3 to 4, you have the heat exchanger, that is combustion chamber. Okay. So two heat addition process, one is from the regenerator and one is from the combustion chamber. And this is the Brayton cycle with the regenerator. And if you have questions about this one, you can ask. Otherwise, I will move on to next. Okay, good. So now comes the Brayton cycle with the regenerator, intercooling, and the reheater. And now let's draw that one here and to see what happens. So here you will have that this is the one. And now let me write the component names. Okay, then I will analyze it. So here you have the compressor one. Okay, and this compressor one increases the pressure from 1 to 2. Okay, and then you have the intercooler here. Okay, so if you remember from our previous lectures, we have said that. So what is we have looked for the work done by different type of the processes. You have isothermal, polytropic compression, polytropic, and two-stage polytropic compression. And you have seen that. So the best efficiency is with this one and with that one. Okay, this one is not always possible. Okay, and therefore we are using this one. Two-stage polytropic compression. And this one means that so here you can see that pressure is constant, and here you will have that cooling process. And now we are doing the same stuff here, and I am adding intercooler between compressor 1 and the compressor 2, and the temperature is dropped. Okay, and then you have the second stage by the compressor 2. So you will have that 3, and then you will have that 4. And then this 4 outlet of the compressor is diverted to regenerator here. Here you will have the regenerator. And the temperature is increases. You have the value 5. And then you have this combustion chamber. Okay. And this from 4 to 5, you have this regenerator. From 5 to 6, you will have this combustion chamber. Okay. And here you have also the temperature increase, which is 6 is more than 5. And then you have come to turbine 1. Okay. This turbine uses energy of the fluid at state 6. And then outlet of the turbine, you will have that state 7. And then here I am adding the reheater. So what is the purpose of the reheater? So the outlet of the turbine, so it has low energy. Okay, but it is not so low. So let me talk about state 7. Okay. But we can use that energy. Okay, we can use that energy again. So to be able to use it again, so it has high pressure, high P, but low temperature. So it has high pressure but low temperature. What you are doing is that you are sending it, sent to reheater. Okay, the name says it. You are reheating it. The temperature increases, and but P is constant. Okay, and then now comes the turbine 2. You will have this turbine 2 after this reheater process. So you will have 8 here, and now comes that turbine 2, and then you will have this 9, and 9 goes from the turbine outlet to regenerator because it has energy. This one has an energy, so it means that you can utilize the energy of this one to heat. So you can see that here. So you are heating the outlet of the compressor. So it makes this one makes the work of the combustion chamber less. Okay? Because if you didn't use this one, you have to increase the temperature from 4 to 6. By adding the regenerator, you are increasing from 5 to 6. You can see it in the previous chart here. So from 3 to 4, you have the combustion chamber. But if I didn't use the combustion chamber, I have to increase the temperature from 2 and 4. You can see the temperature increase, but the regenerator helps me for the temperature increase. Okay, so then you have the 9 that goes from the turbine outlet, and then you have this 10 here, which is the outlet of the regenerator. Okay. Now let's draw the TS diagram again to see what happens. You have this temperature here. You have this entropy here. This is the TS diagram. And I will start from the compressor 1. And as always, so I should add these two statements here. The compressors and the turbines are identical. Identical means that they work with the same pressure ratio and they work with the same temperature ratio. Okay, now let's start. So I will have that state 1 or the compressor 1. And this one increases that is the temperature to state 2. This is state 2. Okay, and then comes that intercooler. Okay, this intercooler that cools the temperature of the turbine compressor. The compressor temperature should drop from T2 and back to T1. It will drop it. But here you should remember that if you remember this, delta S is the change of entropy is equal to that Q in, let me raise this stuff here. So you will have that in minus out plus the generation. Okay. And for this relationship, if you remember that out was for entropy, Q out by temperature, and you have also mass, so that mass times this entropy. Similarly, here you have that Q in and by temperature, and you have this mass into entropy. For the intercooler, you can see that it is out property, because here you are giving off the heat of the compressor outlet. So here you are having the opposite of the regenerator. You can see in regenerator, you are giving heat to the compressor outlet, but for intercooler, you are giving the temperature of the compressor, you are dropping the temperature of the compressor outlet. So therefore, this one should decrease the entropy of the fluid. Okay. It decreases entropy of the fluid, but increases entropy of the environment. So at the end, the total entropy increases. Okay, so now let's go back to here. From 2 to 3, you will have this process. Again, back to state 1. You can see it's again back to state 1. Let me erase that part, and to make that everything is all right, so I will add this state 1 temperature here. You can see this one is that state 1 temperature. And that intercooler cools the process by decreasing the entropy back to state 2. You can see state 3, sorry. You can see that state 3 here. So the temperature of the intercooler has dropped it to 3. And then from that 3 to 4, we'll have the same process here, again with isotropic process. And we will have the same temperature here again for the, you can see that same temperature here. Okay, and then you will have this temperature here, which is 4. This is the outlet of the compressor. Let me draw that one too in that color. Okay. And then from 4 to 5, regenerator. Regenerator, if you remember, you have said that the temperature increases. Okay. The temperature increases, entropy increases, but the pressure is constant. Regenerator, all heat exchangers in ideal analysis are isobaric. Therefore, from 4 to 5, you will have that increase in temperature and entropy. From 5 to 6, again, you will have that increase in temperature and entropy. Okay. And then from 6 to 7, you will have that the first work of the turbine 1. Let me draw it. So that work of the turbine 1, it will drop the temperature value because it uses the energy of the fluid, but the entropy is constant because it is reversible and adiabatic. But the 7 is more than 5. Okay, you should remember it because it is that in the perfect cases that 7 is the same as 5. And anyway, so if I draw it, so you will have this chart here. It is from 6 to 7 here. This is the turbine 1. And then comes the reheater. Reheater, you can think of this as the opposite of the intercooler. The intercooler drops the temperature to 3, but the reheater increases the temperature to back to same state. Okay, so therefore now after the reheater, here you have the Q addition, heat addition. You can see it is the heat addition to the fluid here. The fluid increases, fluid temperature is increased. So you are going back to the same state here. So you should have the same temperature but the entropy should increase. Now let me draw it. So you have that entropy increase. You can see that entropy increases, and you have got back to the same state. Sorry, 8. The 8. You can see that entropy increases, temperature increases, but this one is also isobaric. These are all heat exchangers. This heat exchanger. And this one is also heat exchanger. This one is also heat exchanger. And then again, the turbine 2 comes into the picture, and it drops the entropy. It drops the temperature, but entropy is constant, and you have that this null. Okay. And here you have the isentropic process, the reversible adiabatic, and from the 9 to 10, that the fluid gives off its energy, okay, and it drops to the value of that it is more than 4. It should be more than 4 here, so that you will have something like this one. Okay, if I'm all right, this will be the 10. Okay. And then let me raise it a bit more than that to be sure that it is more than 10. 4. Okay, this one will be that 10, state 10. But to make the process as the thermodynamic analysis, this one should be closed. So at the end, it is for our case, because if you are doing a deeper analysis, you cannot make it as closed cycle. It should be closed cycle here, and to make it closed cycle, I am adding a heat exchanger here, so that this heat exchanger HX, and this HX drops temperature. Okay, so that drops temperature, and you will have that this state of the fluid, okay, and you will have that state back to 1. Let me draw it if I am able to draw it. Okay, you can see that this is by HX. Okay, and you see this is the cycle for the Brayton cycle with regeneration, intercooling, and then reheater. Okay, the process direction, you can show it. It is in that way. Okay. Similarly here, the process direction is in that way. You will have that process. And for this one, the process direction is shown. Okay, this is how we draw the TS diagram for the regenerator and the intercooling and the reheater cycle. But we have talked about this one. If you add more components, it increases the weight, and the more weight means that it makes disadvantages. Okay. Okay, so let's solve an example. We have that Brayton cycle with the regenerator, intercooling, and the reheater example. Okay. This one actually without regenerator. So this one is a simple Brayton cycle. Okay. These components are not there. This one is not there. We have a Brayton cycle and the simplest one. It says that we have a compressor inlet and turbine inlet temperature with these values. The cycle has a pressure ratio of 8. Determine the unknown enthalpy values, backwork ratio, efficiency of the cycle using air standard assumptions. Now what I will do is that I will draw the components of the cycle. So this one has a compressor here. Okay. I'll draw it one more time. So you have that compressor. And then from this compressor, you have this, that is heat exchanger. Sorry, that combustion chamber. So the combustion chamber at the end, it's also heat exchanger. This one is that combustion chamber. And then from combustion chamber, you will have this turbine. And then from turbine, again, you will have this heat exchanger here. And that way, this way. And this one is compressor 1. So there's only one compressor, therefore no need to add one here. And this one is a turbine. Okay, here you have the state 2, and this one is the inlet state 1, state 3, and the state 4. This is the general cycle, and the question says that the compressor inlet temperature is T1, is 300 Kelvin, and the T3 turbine inlet temperature is 1300 Kelvin, and the cycle has a pressure ratio of P2 by P1, and you can show it as PR, which is 8. Determine the unknown enthalpy values, backwork ratio, and the efficiency of the cycle. So firstly, we will use always for the cycles. The best thing is that we have to use the Gibbs phase rule. Therefore, I will draw the cycle here so that you will have that 1, you will have that 2, and the 3, and the 4. And I will look for which components are okay for me to find the required properties. Okay, so here you will have this components here. Let me see. And then given values, I don't know. So here you have that pressure, the temperature. I can add the specific volume. I don't know if it is not given in the question, but let me add it, that you will have that entropy and the enthalpy. Okay, for the process 1, the first process, you have that temperature is given, okay, which is 300 Kelvin. Let me do that. So here you have that pressure is given. Sorry, temperature is given. And you have that temperature given for state 1. For state 3, you have that also, which is that, and the temperature 3 is given, which is 1300 Kelvin, and the P2 by P1 is given, which is 8. Okay, now let's see what we can do for this process here. Okay, so for the state 1 and the 2, it is isentropic. So that means that, and this one, this one has a entropy of S1, and this one has also entropy of S1. Okay, good. So what else can we solve to have the, and for the state 1, I can find the enthalpy, because the enthalpy is only a function of the temperature. So here the question says that to find the enthalpy value, therefore for state 1, it is okay. I can find the enthalpy. Now let's finish this cycle here, so that from that state 3, I don't know anything, but I know that state 3 and the 4, they are also isentropic. If you have an entropy here, which is S3, you have the same entropy here. Okay, this is the general view of the table. Okay, now let's try to which states we can find the enthalpy values. Enthalpy is a specific form of the Gibbs phase rule here. Enthalpy is function of T only. Okay. Enthalpy and the U for ideal gases. Therefore, 2 independent intensive properties may not be required if you have the temperature value. For state 1, I can find the temperature value, because here that enthalpy is function of the temperature, and therefore I can find enthalpy as a function of temperature 1. Okay. Now to find for the state 2, the enthalpy values, and let me add one more column here, because that isentropic relations will help me see. Okay, and that column will be at PR. Okay. So that for state 1 also I can find the PR value, because PR is function of temperature only. I can find the PR value. And since I know the pressure ratios here, so that P2 by P1, so for state 2, okay, I know that P2 by P1 is equal to PR2 by PR1. Okay. And the P2 by P1 is given in the question, which is, this one is given as 8, which is 8 here. Therefore, PR2 by PR1 can be easily determined, and since I can find the PR1 from the given temperature, so this one will be that PR will be a function of the temperature at state 1. Okay, so from here I can find the PR2. So that PR2 for state 2 can be found. So if I find the PR2 for state 2, then from this PR2 value, I can find, so by pressure ratios. Okay, this one is isentropic relationship, isentropic. So from that one, I can find the PR2, and from PR2, I can find that enthalpy, which is function of PR2, and you can also find the temperature, which is function of the PR2. Okay. Now comes that state 3. For state 3, I can find for the enthalpy values, because enthalpy is function of temperature at 3, and the PR is also function of temperature at 3. We can find these two properties. And for state 4, okay, what I will do is that I will find that PR4 divided by, let me see if we can solve that PR3 will be equal to that P4 divided by P3. Okay, this is for, sorry, that is for state, okay, that is true for state 4. So what I will do is that PR4, I can find it. It is PR3, I can find it, it is given. And the PR4, so I should find this one. And the P4 by P3, let me see which one is given here. P3 is same as P2 because it is isobaric. This one is isobaric because it is heat exchanger. And this one is also heat exchanger, isobaric. And the P3 is same as P2, and you have also that P4 is same as P1. Okay. And from here, you can see that these two property ratios are also known because P2 and the P1 ratio is known. Therefore, I can find this value here, and from that one, I can work out this PR4 value. So PR4 here can be found by pressure ratios. Okay. And then from that pressure ratio, I can find, this one should be at the upper part of this chart here. So I can find this PR by pressure ratios. And then from that PR, I can find the enthalpy value, which is function of PR4 only, and the temperature, which is function of PR4 only. You can see that I have worked with a specific case of the Gibbs phase rule, where that enthalpy and the internal energy are function of temperature only. And you can see that I have only found the properties that are one function of the temperature only. Because here I cannot find the nu, I cannot find the pressure. Because here for pressure and the nu, I need two more properties. Okay. Here I have worked with the specific part of the, so here we worked with specific case of Gibbs phase rule. And the specific case of the Gibbs phase rule says that for that enthalpy, internal energy, and the PR for ideal gases, okay, one temperature value is enough. T is enough. Okay. For this one, the temperature is enough. Therefore, you can see that I have only worked with these columns here, which are the functions of the temperature only. Temperature, enthalpy, sorry, that enthalpy and the pressure, PR ratio. For the other columns here, so this one, I cannot find it. This one, I cannot find it, okay? Because these are that, for this pressure and the nu, for P and the nu, and as well as entropy, okay, as well as this entropy values, so I need two independent, intensive properties. Therefore, it is impossible to find these two properties here. Okay. But only the possible case is that I can find the properties that need one known value, which is the temperature. Okay, so let's solve the problem now. So the solution process will be a very easy part because the values are, the process is known. We will just use the table. Therefore, I'm leaving this window here. So I will share Okay, that entire window, and then I will use the tables. Okay, and we are only working with this ideal gas, which is air. Now I'm going to the air chart here, which is A18. So let me go back to that chart. A17. For A17, for the ideal gas properties of air, I will just start from the first part. The first part says that I know the temperature, I can find the enthalpy values. And enthalpy is function of the temperature only. And the T1 is given, it is 300 Kelvin. So for that 300 Kelvin, that enthalpy is in the second column, which is 300.19. Let me write the values here. So we just make a value. We write that enthalpy is from the chart. Okay, this is from the chart. It is 300.19 kilojoules per kilogram. Okay. Now the first state is okay. Now comes the second state. For the second state, I should find that enthalpy value, but I will use the pressure ratios. Okay. Therefore, this one is for state 1. And let's do that for state 2. State 2, I will need that P2 by P1 will be equal to that PR2 by PR1. Okay. And the P2 by P1, it is given in the question, which is 8. So this ratio is 8. And the PR1, I can get it from the chart because at 300 Kelvin, this one is 1.38. So from A17, so that's 1.386. This is the PR value. And then from that one, I can find that PR2 value. Okay. And the PR2 value for this one will be equal to 11.09. Okay. This is the PR2 value. And now I will go back to the chart again, because if you remember the process here, that enthalpy is function of PR2, temperature is function of PR2. So therefore, if I know the PR2 value, I will find the rest. But it is specific case for Gibbs phase rule because I'm only working with one property that's function of temperature only. So from this one, again, I use the A17. Okay. And let's go back to A17 and to the pressure value of 11 point something. That is this column. We have that 11.10 and the 10.37. So let's work out. You can see that the values are very close. Therefore, no need to make any linear interpolation here. It is just that you will have that temperature will be 540 Kelvin and the enthalpy value will be equal to 544.35 kilojoules per kilogram. And this is for the state 2. Okay. Now comes the state 3. Let's solve for that one. I will use a different color. State 3. For state 3, so the question says that to find the property that's at state 3, so you have to again find the PR, and the temperature 3 is known, which is 1300 Kelvin. Now let's work it. That T3 is 1300 Kelvin. Okay. And if I go back to the chart again, you will see that for that temperature, you can see the PR is okay, that you can find it, and enthalpy value is okay. So therefore, I can find that enthalpy value, which is equal to that. This is the enthalpy value. And then the PR value is at state 3. Is at 30.9. It's dimensionless, of course. This is for state 3. Now comes that state 4. For state 4, I will use this pressure ratios. PR4 by PR3 is same as P4 by P3, and you see that we have said it, they are the same. So let's do that for state 4, and you will have that PR4 by PR3 will be equal to that P4 by P3. We have said that P4 is same as P1, and the P3 is same as P2. Okay, and the P1 by P2, it is the opposite of this one. It should be that 1 by 8. And the PR3, we have found it, and now comes that PR4. PR4, you can find it. PR3 is given here, which is 330.9. And if you do that calculation, you will have that 41.36. Okay. Now I'm again going to the chart here for that value of the PR4. Okay. Let's go back to the chart. PR4 value, which is 41.36. You can see that it is, you have the value here, is in between. Therefore, you should use this linear interpolation stuff. Okay. And if you use that linear interpolation, you will find that from A17, okay, that the temperature at 4 is 770 Kelvin. We'll go back to here, and you will have that in between, 770 Kelvin. That will be the temperature, and enthalpy at state 4 will be equal to that 789.37 kilojoules per kilometer. This is the state 4 values. Now you see that I have found all of the values. So for the state 1, for state 2, for state 3, and 4. But you should always remember that this one was a specific case of Gibbs phase rule. In this specific case, we only needed one, which is a temperature. Okay. But if you need that general case for Gibbs phase rule, you have to find the pressure. To find, for example, pressure, mu, and entropy, you need two independent properties. Because for ideal gases, the enthalpy, internal energy, and the relative pressure is function of the temperature only. Okay. Since that H is function of temperature only, U is function of temperature only, different function, and the PR is function of temperature only. And see that they are the functions of the temperature only. Therefore, it was a specific case of the Gibbs phase rule. Now we have found the enthalpy values. Now the question says that Backwork ratio. So I will ask this question for you. If you remember, what is Backwork ratio? You can write it as a comment so that I can see. What is Backwork ratio? If somebody remembers. What is Backwork ratio? Nobody remembers. That's good. Backwork ratio is, this one is, so R backwork. It shows that the work of compressor divided by work of turbine. Because some of the compressor work is supplied by the turbine, and this compressor and the turbine, there is a shaft here that connects these two to supply the turbine, some of it, to the compressor. Okay, now let's find the compressor work here. And who can say that what is compressor work? And by using the first law, what is the compressor work here by using the first law? Okay. So that you will have that compressor ratio, compressor work, it will be that H outlet, the enthalpy is higher than the H2 minus H1, and divide by the work of the turbine. Again, by using the first law, you will have that H3 minus H4. And we know that H2 minus H1 and these values are given. So let me write it. H2 is 544. You will have that 544.35 minus H1 value is 300.19, and divide by H3 value is that 1395.97 minus H4 value is at 789.37. That is the backwork ratio here, and this ratio will be equal to, if you calculate it, is 0.40 or 40%. So what it means that 40% of that work of turbine that is used for drive the compressor. Okay, so 40% of the work of the turbine is used to drive the compressor, and the rest, for 60%, generates electricity. Okay. But it is not the 60%, but if you calculate it, and you will see that, and due to efficiency problems, it will not be 60%. And due to efficiency, it will be less than. Okay, so this is the backwork ratio. So we have found it. So the question says that at the end, efficiency of the cycle. Let's do that. Eta of the cycle will be that it is 1 minus Q out by Q in. Or, so this cycle is like this cycle is at the end a heat engine. This is the Brayton cycle here. For that Brayton cycle, you have that some Q, so that source. And for that Brayton cycle, you have this sink. Okay, and then here you have this work net. And for the source, you will have that Q in. For the sink, you have that Q out. Okay. So then you will have that efficiency will be equal to 1 minus Q out, Q in minus Q out by Q in. So that one can be written as Q in minus Q out divided by Q in. Okay. And the Q in minus Q out, if you do the cycle analysis here, so that if it is cycle, it first law says that you have that in is equal to out. Okay. And therefore that Q in, which is the in, should be equal to Q out plus work net out. Okay. Therefore work net out will be equal to that Q in minus Q out. Therefore I can replace this one as that work net out divided by Q in. Okay. And the net work out from the system is only 60%, because the rest 40% is used for the compressor. It will be that 60% of the work of turbine. That is the work net out. And the Q in value is, so we will calculate the Q in value, and the Q in value is that you will have that H3 minus H2. That will be H3 minus H2. That is the Q in value. So therefore you will have that 0.60 multiplied with the compressor work, the turbine work, which is H3 minus H4. Can calculate it, it will be that 606.60 kilojoule per kilogram. And divided by the Q in value, which is H3 minus H2, that will be the value for Q in, which will be 851.62. And this one will be that 0.43. So you have that 43% efficiency. Okay. So this is the efficiency that you have got from the cycle, and this one is this is the maximum efficiency, but in reality it will be lower. So, but here I will add some more stuff for the Brayton cycle here. So that for the Brayton cycle, if you remember the graph here for the ideal one, you have the 1 to 2, and the 2, 3, which is the heat addition. 3 to 4, you have the temperature drop, and then from the 4 to 1, you have this back to the process again. Let me do the cycle again here. I will redraw it. So you have this, that temperature diagram versus entropy. Okay. And first comes the compressor, where it compresses from 1 to 2 in an isentropic manner. And from 3 to 2 to 3, you have this combustion chamber. From 3 to 4, you have this turbine, and 4 to 1, you have this. That is the heat removal. Okay. Here you have that heat addition to the system. This is the thermodynamic analysis. You have that Q in, and you have that Q out. You have this work out by turbine, and this one is the work in of the compressor. This is the real one, but if we look at the ideal one, if you look at the real one, what you can see is that. Okay, now let's see actually let me draw it over that one. Let's overlay the plots instead of drawing one more. In the reality, what will happen is that from 1 to 2, you will have so this one is that P2 and the P3 are same. P2 and the P3 are same, and it is isobaric. Similarly, here you have that P1 and the P4, and it is isobaric. Okay. But in reality, what will happen? The compressor from 1 to 2, it will not be isentropic. You will have that entropy increase. This will be for the reality. Okay. Here you will have that 2 prime. Let me draw a different line here so that nobody gets confused with this line here. Okay, this one is the isobaric line, and you can see that in reality it will be different. You will have that this chart where you will have the change in the entropy, and the entropy will increase. Okay, and this one is that the working compressor. And from 2 prime to the next state here, it will not be isobaric. The pressure will drop. You will have something like this one. Okay, and the pressure will drop to the value something like this one. Okay, and here we'll have that 3 prime. Okay, and then you will have that from 3 prime to 4. If it is isentropic, it will be that manner, but if in reality it will not be isentropic, but it will be. I will have to change the place of the 4 again. I will add that 4 here, not the lower part of it. So 4 should be there. And for the reality, for the real one, that from 3 prime to 4, you will have this entropy increase. Okay, and this one will be that 4 prime, and then back to 4 prime to 1, you will have go back to the similar process, but here again you will have this pressure increase. Okay, this is the real one. 1 to 2 prime, and that's for the 3 prime. Then you will have that 4 prime and back to 1. Okay, this is the real. But for the ideal, you will have that 1 to 2 and the 3 and the 4. This one is back to 1, and this one is ideal. Okay. What happens in reality? In reality, it happens that from 1 to 2, this one is the compressor. So you will have that entropy increase, okay, due to friction. This is from etc. Okay, from 1 to 2 compressor. This one is the real. From 2 prime to 3 prime, so you will have that pressure drop in heat exchanger pipes. Okay, this is the 2 to 3 prime, and from 3 to prime to 4 prime, you will have that entropy increase. This is a turbine. You will have again that entropy increase it is due to friction, etc. Friction is not the only thing, but it is one of the main ones. And from the 4' to 1, you will have that P increase in the exchanger. Okay, you will have this process. This one, that one, and this one, and that. Okay, this will be the process that we are going to have. Okay. These are the real ones, but this is the ideal one. Okay, and the one more stuff about the Brayton cycle that should I add it here is that so eta of the Brayton cycle, let me write it here. The eta of Brayton cycle, and for any heat engine, it is that 1 minus Q out by Q in. Okay, and this Q out, it is so that before on the Q in part, which is this one. Okay. This Q in part is related to the temperature increase, which is T3. Okay. Here you will have that temperature increase from 2 and 3. Okay. Therefore, more efficiency means that you have higher temperature. So higher eta, you will have that higher temperature, T3. Okay, but you cannot increase the temperature of the air to higher amounts because you have that limitation on T3. Okay. And the limitation on T3 is due to the material of the blades. Okay. So if you increase the temperature, you will have that higher efficiency. But that higher efficiency is limited because that if you increase the temperature, the blade materials, you have to select the blade materials such that they can endure this higher amount of the temperature. But it is not possible because the blade materials that you are having here, that there is a limitation. Okay. So that, for example, that it should be 1000 degrees or that it can be that 900 degrees. But anyway, there is a limitation on the selection of the blade material due to the amount of the temperature here. There are also some efficiency increase for the Brayton cycle. We have talked about in our last two lectures, which is that regenerator, intercooling, and reheater, and also Brayton cycle with regenerator alone. Okay. This is the general overview of the Brayton cycle, but you should remember that we have only worked with this that is real one, the ideal ones. Okay, but in reality, it is much more complex than this one. And the one more stuff about the Brayton cycle that before I forgot is that effectiveness of the regenerator. Okay. Which is epsilon. So if you go back to the regenerator here, this regenerator, it can have that effectiveness. In other words, it means that efficiency. Okay. So in the real conditions, it can increase the enthalpy of air from 4 to 5. Okay, but in ideal conditions, that you can have that maximum increase for this 5 value outlet of the regenerator. Okay, for this 5, and the effectiveness of the regenerator is determined by. Let me first write the energy balance for this one. You will have the 4 inlet and the 5 outlet, 9 inlet and the 10 outlet. So this one is the regenerator. You have that 4 here. You have this 5 outlet. You have this 9 inlet, and you have this 10 outlet. Okay. And if you write the first law for the regenerator, and the kinetic energy changes, potential energy changes. Okay, they are approximately 0. So for that case, you will have that H5 minus H4 will be equal to that H9 minus H10. And the maximum regenerator efficiency can be that H9, this one, lives at the enthalpy value of the H5. Okay, you have the, so the maximum is that H9. We have talked about this one. is at the same enthalpy value of the H5, the maximum. So instead of that one H5, I put it as that H5 prime. H5 prime means that, so this one is ideal. Okay. But in reality, we have talked about this one, so that H9 will be greater than H5, and also the enthalpy at state 10 is more than enthalpy at state 4. So for the effectiveness, we are comparing the maximum conditions with the minimum conditions, so for the real conditions. So that for the ideal conditions, you will have that H5 prime, which is the enthalpy difference, and then you will have that H5 prime, and that one minus with H4. This is the ideal one, but in reality, it happens that H5 minus H4. This is the effectiveness of the regenerator, the maximum difference between the enthalpy value change and divide by the maximum difference, so that the real difference. Okay, this one is that delta H of real, and this one is the delta H of ideal. And if effectiveness is 1, it means that it is that reversible, perfect, or ideal. Okay, but in reality, effectiveness is less than 1. Okay. And this is for the regenerator. Okay, this is for the Brayton cycle, and I should say that for the better analysis, you have to include the losses, isentropic efficiencies for the cycle. Okay, with this one, I stop the recording, and if you have questions, you can ask.